Mechanics number 3, 2006. This one was a tricky one. So thin hoop, mass m, radius r, rotational inertia mr squared, release from rest from the top of a ramp, length L, ramp makes an angle theta with respect to the horizontal, table is a height h above the floor, assume the hoop rolls without slipping down the ramp and across the table, express all algebraic answers in terms of the given quantities and fundamental constants. All right, so we got some cool stuff going on there. Why do I do that? I pressed the wrong button. All right, I fixed it. So there's actually a couple different ways to do this first part. I did it in terms of forces. You did not have to do it in terms of forces. I think you probably could have done it in terms of energy or kinematics, but I did it with forces. So looking at the forces that are on our hoop, right? If we look at linear forces, right? The forces being exerted on it, we have a gravitational force downward and we have a friction force up the ramp, right? We have two forces being exerted on our hoop. So based on how we do it here, right? I have friction up the ramp. I had the X component or whatever component you want to call that of gravity down the ramp. Maybe I call it X, whatever, because it's not the full component of gravity, right? Because it's gravity down the ramp. It actually ends up being a sine function because this is equal to theta and opposite FG times the opposite angle will give us FG sine theta will give us the opposite angle. So that's what we end up with here. We get friction, positive friction minus the sine component of the gravitational force, which is picking out that component that goes down the ramp is equal to m times ACM. And then we get in trouble, right? Because right here, we're like, oh, we were using forces. We were doing so good. But they don't give us a coefficient of friction. They don't tell us anything about friction, really. And we're only allowed to use given quantities and fundamental constants. And F is not a given quantity or a fundamental constant, right? And I don't have any, well, I guess there's a normal force here too, sorry. Let's not forget the normal force. I don't know why I just thought about that, but there is a normal force there. It just doesn't come into play. I was thinking about it because we could substitute mu k times the normal force, but that doesn't really do us a whole lot either because we don't have mu. Mu is not a fundamental constant. So we get in trouble, right? We have this equation, we're kind of stuck. So how do we adjust that? We need to find another equation that we can use that has friction in it that hopefully we can use to cancel that out. Two equations, two unknowns kind of scenario, right? Because I'm looking for the acceleration. That's my one unknown. I need to get rid of this other unknown. So we come to our second equation, right? There's two equations for equilibrium, two equations for forces. Second one has to do with rotational motion, right? Some of the torques. Because this object is not slipping, right? If this object was slipping, we could have just treated this like a regular block sliding down a ramp, but it's not sliding down a ramp. It's going to rotate as it's going down the ramp, which means we're experiencing torque, and we have to think about angular motion as well. So I did some of the torques. There's only one force acting on our object that's going to cause a torque. If we look at what I drew right here, right, gravity acts on the center of mass. It always does. And because our object is going to rotate about the center of mass, gravity is being applied at the rotation point, so it doesn't cause rotation. If we look at the normal force is also being applied through the axis of rotation, so it doesn't cause a torque. But friction is being applied out at the edge here, right? Not along the axis of rotation. So friction does apply a torque, and it will cause our object to rotate clockwise. I don't know why all my stuff is disappearing. Cool. Exactly what I wanted to happen. Now all my things have disappeared. Now my computer's frozen. I think I fixed it. Where was I? So the friction does cause a rotation. It causes a rotation counterclockwise, or sorry, clockwise. If we look up here, right, we are rotating clockwise about our axis because of the friction force. So clockwise rotation is negative in terms of torque. So we get negative friction force. Torques are forces times distance, right? So force times the distance away from the axis of rotation, which would be force times the radius of our hoop, is equal to I alpha. We plug in our value for I, which is the moment of inertia, or rotational inertia, whatever you want to call it, mr squared. So we put in mr squared for I there. R cancels with the R on the bottom. Oh, hold on, I was skipping a step. Excuse me. You notice here we end up, this isn't a perfect equation yet, because we're introducing another variable a here, or alpha, right? And alpha, well, this equation will help us get rid of f, right? Because we could substitute f in, we would just be replacing it with this alpha, which is another unknown that we have and we're not allowed to use. So we can use the relationship between linear accelerations and angular accelerations. The acceleration in the center mass is going to be equal to alpha times r, just like velocity is equal to omega times r and position is equal to theta times r, right? They're all kind of equal there. So we can replace alpha with the acceleration over r, all right, which when we put it in here, it gives us a variable that matches with our equation on the other side, and means we're not substituting in something new, that we're not introducing another. So we end up with 3 equations and 3 unknowns is essentially what we're working with here, right? We have our force equation, we have our torque equation, and we have our acceleration equation. We use all 3 of those in order to kind of narrow it down, so we end up with just an equation that we can use to solve for acceleration. So we plugged in I, which was mr squared. We also plug in a, which is the linear acceleration over r. R cancels with r. R also cancels with r on the other side, and we get friction. Moving the negative sign to the other side is equal to negative m times the acceleration of the center of mass. Then we can take this now, plug it in for our friction over here, right? So we get rid of friction. All we're putting back in is mass and acceleration, which are 2 things that we already have. Mass is a given constant, that's allowed to be there. Acceleration is what we're looking for. That's obviously allowed to be there, so that's all good. So we plug that in for friction. So we get MACM minus mg sine theta equals m times the acceleration of the center of mass. Everything has an m, so we can cancel it. And we get negative acceleration of mass minus g sine theta equals the acceleration of the center of mass. Add that to the other side, becomes, I don't know why I made that negative, positive 2. And we get the acceleration of the center of mass is negative g sine theta over 2. The reason I've gotten a negative here is because I'm assuming the acceleration is downhill, right, in the negative direction. So I took down to be negative. I mean, you could have just as easily said down the ramp is positive, and you would have ended up with a positive g. I think either or is fair. All right. Derive an expression for the speed of the center of mass of the hoop when it reaches the bottom. Now that we have an acceleration, we can use kinematics to just figure out what the speed is going to be. We use the v squared v naught plus 2a delta x equation. This is the speed that we're looking for, this v. V naught was 0 because we started out with 0 velocity. We plug in the acceleration of the center of mass that we just solved for. We can plug in L, which is the distance that it's going to travel, right, down the ramp here. The nice thing is about this is because we figure out the acceleration of the center of mass, right, we actually figure out the acceleration in the L direction. So we don't have to worry about like messing with cosines or sines in terms of L, because that's the displacement it's undergoing. It's the acceleration and the displacement are in the same direction. So we just multiply by L there. 2 cancels with 2, take the square root, and we get the velocity will be g sine theta times L square rooted. Derive an expression for the horizontal distance from the edge of the table. So this is kinematics again. This is basically a projectile motion problem, right? We know our object is being projected off of a surface with an initial speed square root g sine theta times L. How far is it going to go down here? We have to use the y equations, y components to solve for time. Obviously, we don't have numbers, so it's not as easy, or it's not quite as easy, but we solve for time here. We take that, we plug it into our x equations so that we can find the horizontal distance. X equation is just going to be vi times t because we don't have any acceleration in the x direction. Initial velocity is the velocity that we solved for right here. So we plug that in, we plug t in, and we get square root g L sine theta times what we got for t, which is square root h over g. G cancels with g because they're both under square root signs. We can just combine the square roots and we get the displacement in the x direction is 2hl sine theta. So we have our answer for the distance traveled by our hoop in the x direction. Suppose the hoop is replaced by a disc. How does the distance from the edge to the where the disc lands compare with the distance for the hoop? It will be greater than, and the sole reason is because the moment of inertia for a disc is less than the moment of inertia for a hoop. Moment of inertia for a hoop was mr squared. Moment of inertia for a disc is 1/2 mr squared. So if we take that 1/2 and we kind of work it through what we just did, right? There's a 1/2 right here. That means that F is equal to 1/2 MACM. When we plug it over here, there's a 1/2 instead of a instead of just a ACM, which means when we add it to the other side, we're only adding a 1/2, which means when we divide back over, this 2 is a smaller number, right? That 2 is not as big because instead of adding 1 to the other side, we're adding a 1/2 to the other side. So we only get 1/2, or we get 3/2, right? Because we get 1 plus a 1/2. So this 2 becomes a 3/2. And when we divide the 3/2 over, this number for our acceleration obviously becomes bigger, right? If we're dividing by 2 versus dividing by 3/2, this acceleration would become 3g sine theta over 2, which is a larger number than g sine theta over 2, right? Did I do that right? It would be 2. It would be 2/3, I think. Still, 2/3 is bigger than a 1/2. It is 2/3. It would be 2/3. So 2/3 g sine theta is bigger than 1/2 g sine theta, which means our acceleration is bigger, right? And if our acceleration is bigger, what happens is velocity, that velocity gets bigger. If that velocity is bigger, what happens to this distance? This distance has to get bigger. So that's kind of what I explained here, right? I for a disc is smaller, which will lead to a larger acceleration down the ramp, larger final speed at the bottom, which means the horizontal velocity as the disc leaves the table will be greater and lead to a greater distance traveled by the disc than by the hoop. It essentially boils down to the fact that because the disc has a smaller moment of inertia, it's easier to make it start rolling. And because it starts rolling faster, it's able to roll faster when it reaches the bottom, or be faster when it reaches the bottom, because it's easier to cause that acceleration to happen. And we just get something that's moving quicker, right? And if it's moving faster, then it has more acceleration. It has more acceleration, its final speed is going to be greater. If its final speed is going to be greater, it's going to go farther when it leaves the table. And there is question number 3. Let's just sit for a second while I figure out how to stop the video.